Hello, everyone, and welcome to our first Haikubox webinar. This is being recorded, and we will post our expectation is to post this to our YouTube channel in the coming days. But we're glad to have you here. First, I always need to thank our sponsor because without funding from the National Science Foundation, Haikubox really wouldn't even have been possible. So we are grateful for the support of the NSF, the SBIR program. We're glad you're here. Everyone is muted, but we expect to have time at the end for questions. I want to introduce David. So he is the Haikubox founder. He's our chief scientist. As a company of 4 people, we all wear a lot of hats. So he does all kinds of things in addition to science and leading the company. But so David's background, he like me, we didn't know each other at Cornell, but we both went to Cornell University. He grew up in Syracuse, so he spent a lot of time as a kid actually at BB Woods looking at birds. And then after undergrad, he went to MIT and the Woods Hole Oceanographic Institution, where his PhD thesis was on sound-producing fish. He did a postdoc at University of Maryland, and where he studied hearing of fish. And so his focus, and then he was a faculty member at University of South Florida. So his focus for many, many years has been on bioacoustics of animals, starting with animals in the water. And our company still does a lot of manufacturing of things for scientists who are doing bioacoustics in water. But he knows a lot about sound, he knows a lot about hearing, and he's going to share that with us today. And I know all this because we're married for 30-something years. So anyway, I'm going to pass it over to David, who's going to talk about how to read a spectrogram.
Thanks, Amy. Thank you all for being here. We're going to try to hold a series of these webinars probably every couple of months or so. And so I just kind of wanted to thank you all for being early Haikubox supporters and also giving us feedback on things we can do to make it better. Today, I'm really just going to talk about spectrograms and kind of how I use them and how I use them with the Haikubox website. In the future, we'll talk about how Haikubox actually works because it's rather complicated, but I know some of you have questions about that as well. So let's get started. So first I'm going to talk about sound, and there are no equations in this talk, just graphics. So when a bird sings, right, it's pushing air through its syrinx, making beautiful sounds, and what's happening is the sound wave is actually caused by vibrations in the syrinx, and then those are being radiated out of the mouth, and it's actually moving the air particles in this longitudinal wave, and that's what's reaching us. And so the top here is just showing you in slow motion. This is what actually a tone, this is what a tone would look like. And then this blue signal here below is actually what the signal that came out of a microphone would look like. So when that hits our ears, okay, it doesn't come flying in like this, but our eardrum is actually going back and forth with this sound wave. And that moves our 3 little middle ear bones and then stimulates the cochlea. And then that's when the magic in our brain starts going. So the cochlea itself, this is where the sound is coming in. We have tiny little neurons called hair cells all along the cochlea. And the cochlea is called tonotopically arranged, meaning at this basal end, you have 20,000 hertz, extremely high frequency. Actually, no one can hear that. Like little babies can hear maybe 18,000 or 19,000. And then as you go around the cochlea, all the way down to the apex here, like this 200 hertz is like, boo, you get towards the lower end of our hearing. And so this is what really determines the frequency ranges that we can hear. Other animals can hear different frequency ranges than we do. So after it goes to the cochlea, the signal is going up this 8th nerve to the brain, and then the brain is trying to make sense of what it's hearing. So when I'm going to talk about the history of kind of spectrograms and visualizing sound. So, a long time ago, people would try to set the sound of birds to musical notes. And so if you know music, right, so you can know like higher up on the bar is a higher pitched sound, and there's different lengths of the sounds, and there's rests in between them. So you can kind of approximate sounds that birds make, but it's not going to be super accurate because the vocabulary of music isn't as broad as the different kinds of sounds that birds can make. So one way of dealing with this is, try and make this go away, is with a mnemonic, which is being hidden here by this unmovable slide. So the tufted titmouse, so a mnemonic for this might be Peter, 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 right? So this is a spectrogram from a tufted titmouse in Haikubox. And so as we play it, right, so we have time on the x-axis and frequency or pitch here on the y-axis. So I'll play it again, and you'll see these 3 notes as you hear them. Okay, so we'll come back to this in a sec. So going back to the 1950s, before there were digital computers, there scientists, and also driven a lot by the Navy in World War II and listening for submarines and other sounds in the ocean. They were trying to develop techniques to actually visualize the sound, because I think scientists figured out that there were things that they could see in the sound wave that we couldn't really hear. Certainly for things like high frequency echolocation of bats and dolphins and things, it's above our hearing range. So this is an image from the 1950s from the Cornell Lab of Ornithology. And L. Irby Davis here is using a K sonograph. And this is an entirely analog device. So you basically have your recordings of birds or whatever on a tape recorder, and you play them back to this machine, and on this drum there is heat sensitive paper. So it's kind of similar to like the seismographs that you see in museums and things. So that thing would rotate, and you would play the sound through, and it would basically filter the sound just like the cochlea does in different frequency ranges, and then burn this paper with a heat lamp as it rotated. And so every time you wanted to change the setting of the spectrogram, you would have to play it back and burn another piece of paper. So it was incredibly time consuming. So fortunately, we don't have to do that anymore. We can generate spectrograms on the fly. So I'm going to just show you some common signals and what they would look like in a spectrogram and play them for you. So, and don't worry about the numbers, but I'm just going to tell you this one's 500 hertz. So that means 500 cycles per second. It's going back and forth. Okay, so that's about 3 seconds long, and this is what it would look like. If you look at twice as high, 1,000 hertz, right? So now you're twice as high as 500 hertz. The pitch will be higher. And now if we come up to 2,000 hertz and listen, and actually perceptually to us, each one of these is separated by the same amount of frequency. Like this appears twice as high and this is twice as high. But in the spectrogram, you can see they're much farther apart. Okay, so that's one thing about our perception of like frequency space is different than what you would see in the spectrogram. So if we come back to the tufted titmouse, right? So you can imagine this part of the signal up here and down here are like tones, just like we listen to. So you're beep, beep, Peter. So if you play and look at enough of these and know that tones tend to be horizontal, then you can start actually looking at the spectrogram and almost guessing what it sounds like before you play it. So I'm going to give you another example of a tone, but it's a slightly different tone. It's got like a pitch shift to it. So, right? So it sounds kind of a little bit like a hawk. Okay. Now, if we take that similar sound and add what are called harmonics, so basically a whole bunch of frequencies that are spaced evenly from this fundamental frequency down here, you hear this. Okay. So that is our friend, the blue jay. And what I've done is actually, I've just filtered this original signal to only show this one band. And so you can hear how different it sounds, right? It sounds very clear. And then this one is sort of like this menacing blue jay sound that we all know. And we have about 100 million recordings of. So when you look at these tonal signals, right? So if you see a single one, it's going to sound very like whistly. But when you start seeing them as harmonics like this, it's going to be a much more complicated kind of raspy-like sound. So if you think about the like white-breasted nuthatch, and they go wah wah, you'll often see like three frequencies together. Okay, so those were tones. Now I'm going to show you what a more complicated signal sounds like, but we're going to play it at 3 different speeds. Right. So that may be kind of waterfowl sounding, but if we speed that up 2x, it becomes more songbirdy. If we speed it up 4x, it sounds different, and you don't hear at 4x very much of the frequency changes. It's the same sound, I'm just playing it 4 times faster. Okay, so everyone can guess what that is, maybe. That's a chipping sparrow. So this is actually the chipping sparrow song. I've actually slowed it down 2x and 4x. So there's nothing different about this sound except the speed it's playing, but our perception of it from sounding like something that's changing frequencies changes into something more like a trill, like, and if it gets going fast enough, you stop perceiving even the frequency here, and it just sounds like something that's at the frequency that it's repeating at. So a lot of what we hear is our brains trying to make sense of the sound. And that's why it's always good to look at the spectrogram and listen to the sound. Okay, so a different type of signal. So we've been looking at these tonal things and these frequency sweep types of signals. And if you know, another type of call or sound that birds make are calls, right? Which tend to be these very short things that are often vertical on the spectrogram. Anytime you have something that is short in duration and tall, it means it's covering a whole bunch of frequencies very quickly. And so ideally, it would be more like something like a click is going to be very short, but it's going to contain a lot of frequencies. I'm going to switch to Haikubox and just show you kind of how I would look at. So when you get like a yellow rump warbler, and you're like, I don't know if it's yellow rump warbler. What do you do? So I'm going to come over to my Haikubox, and I've just favorited these. So you'll note I have a lot of Haikuboxes. Okay. So here's the palm warbler, and here's the yellow rump warbler. And so if you play them, okay. In addition to the car outside and this other bird, you'll hear the cheep, cheep, cheep. And then if I play the yellow rump warbler. So if you listen to these long enough, you might be able to hear a pitch shift. But if this is your first encounter with these birds, usually what I'll do is I will just go click on eBird here. And And I'll click on listen. And I'll come down and try to find like the chip call, and just see what it looks like for this species. And ideally, there's more. Here we go. And this is a lot easier to do on a computer than it is on the phone. It's possible on the phone, but on the computer, you can open up multiple tabs and you can just line them up all next to each other. So if you look at this closely on eBird, you know, you just hear chip, but if you look at it, you see all of this stuff that looks like it's coming off of it. And this is what is being used by the neural nets to make the IDs on these calls. So if we come back here and click on eBird, we can go look at the yellow rump warbler and share that tab instead. Let's see if we got more. And so you can see again, they're very short, but there's these things coming off of it, but these are coming off at a lower frequency than the palm warbler. Those are really high frequency. So often I will just be bouncing around between eBird and Haikubox to figure out what's going on. So, and often a good thing to do. So let me just go back to favoriting. So say I'm like really into Blue Jays, right? So I'll be looking at my Blue Jays. I'll come through. One thing you'll notice, this H and M and L next to the different detections, those stand for high, medium, and low confidence. So if I'm looking for a really good one, I might come to high and just poke around a little bit. And then say I love this sound, just click favorite and it will save it forever over in this other start section if you want to come back to it. Someone had asked in the questions ahead of time, like how can they actually analyze these data elsewhere? And that's about downloading spectrograms. So you can't download the spectrograms, but what you can do is click this download button and it will download a WAV file that you can then bring into other software to create a spectrogram. And for some birds that are making short calls, so let's see here, right? So this yellow-throated warbler, bunch of detections today. So you might want to look at this because you come pop over to eBird and you're going to come look at the chip calls in eBird, right? And you see this kind of really cool, it looks like almost a paperclip sort of shape. And then you can pop back into Haikubox and go, well, do I see that? Let's see, let me pop around and look at a few of them. You might not really see it, but if you download the signal and bring it into something else, you may be able to stretch it and actually go in and identify it. So, so that's one thing about favoriting is it's a good place to kind of keep track of all of your birds. What was I going to do? Okay, so the calls are those very short things. So let's go look at bringing it all together. So something a lot more complicated than a tufted titmouse or a warbler chirping would be something like the song sparrow. So if you look at this without playing it, you can imagine these things are horizontal tonal-like sounds up here, right? So it might be like, and then there's some of that here, but there's also this kind of more vertical thing in here that might be a little more buzzy. And then we have these 3 or 4 harmonic-like sounds. So they might be more kind of squawky sounding like. So let's now take a listen. Okay, so we'll play it again. So you hear beep, 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 and then this is a trill, and then. So now that you kind of know tones are horizontal, broader band things are vertical, and honky things are harmonic-y, I think maybe hopefully looking at a spectrogram, you can go, oh, that's pretty cool. Sometimes, so this, where was it? Oh, so this was up in Cape Cod, Massachusetts on May 1st of this year. And it's a Cape May warbler. And if I play this, you may not be able to hear it for a couple of reasons. One, there's a lot of other noise in the background, but also you see how high up it is on the spectrogram. It is very high pitched. So as we get older, and depending on what you did in your youth, your high frequency hearing may be fading. So oftentimes you may even see stuff up here that you can't hear at all, but you see on the spectrogram, and that's totally fine. So here, I'll just hop back over to eBird. I'll read about a Cape May warbler, because I'm like, I don't know if I've ever seen one. And then I'll click on listen. And, eBird will often have much nicer looking spectrograms than we will record, often because they're recorded by people using parabolic dishes with microphones in them. So they have tremendous gain and really great signal to noise ratio. And so you can look at these shapes of these songs, just look at a few of them, say, oh, there's a bit of difference here. And you can look at this one. Okay, so I think maybe this first one looked most like it. And then you can pop back over to Haikubox and you go, oh, maybe that was it. So there was another one. Okay, now this one is super complicated. So if you look at this, right, there's more than one bird here, right? So the Cape May warbler ID is based on this. And what Haikubox does, when the neural net returns a result, we show you the top choice. But if you listen, I'll play it again. I think you can hear a red-winged blackbird in the background, but I think there may be something else as well, and I'm not sure what it is. So often, like when you're labeling as well, you may go, oh, this is a red-winged blackbird, not a Cape May warbler. But actually, if you look at the spectrogram carefully, you can see why it was saying that was a Cape May warbler. So yeah, so it gets very tricky like that. I think, so this was very short because I am talking to the void. So Amy had printed out a bunch of the questions that people had at the beginning. And so I was hoping she could remind me of what some of them were. And I'll.
Yes, I can. And I don't see any new questions posed.
Okay.
So I hope that people are able to find how to pose questions. Again, it's the triangle, the square, and there's a little circle down in the lower right-hand side. And when you click on that, then it opens a Q&A, a spot where you can click on Q&A to ask questions. So we'll see if others come in. But one of the questions that someone asked beforehand when they first signed up for the webinar was, are the identifications of species based on more than the 3-second recording?
So no, they are based on the 3-second recording. So we primarily use BirdNet, which is a neural net trained at Cornell University, mostly on the eBird data, but also data from other sources. And that model uses a 3-second clip as for a spectrogram. So just briefly, when the neural net makes an ID, then you're feeding the neural net this like image that we're looking at here, right? And so it's been trained on thousands of these for each species, and it figures out very clever ways to identify what this pattern, what bird this is. And so that's the reason we have 3-second clips here. Is the Haikubox is just bringing in data. We get 3 seconds, and then we will run it through BirdNet, and make an ID on it. I believe Merlin works the same way, except Merlin is probably doing multiple overlapping inferences on multiple 3-second windows, and then goes, oh, did I hear it like 3 out of 5 times? Then I'll call it that bird. So we are probably more permissible than Merlin. And if you look at like even the Blue Jays, a lot of our low confidence ones for Blue Jays are usually right. Whereas if you look at some other species that are less common, which I don't have any of, the lows can be wrong. So we inference on 3 seconds, and that's what you see. So the high, medium, and low is based on the neural net's probability. It's not really probability, it's confidence that it thinks it's that bird.
Okay. Another question we had received was, how does it filter extraneous noises?
So in addition to, let's see. Let me find extraneous noise for you. So what we do is we train on these other extraneous noises. And so we're not actually running BirdNet. Cornell trained a special version for Haikubox where we, so when we started, we were using straight BirdNet, and then we were finding things like plate banging, doors closing, wind chimes were causing all sorts of false detections. And so we added a number of classes to try to get rid of these false detections. So there'll be traffic noise. But anyway, well, here. Okay. So this has insects buzzing in the background, and then a mockingbird calling behind here, very faintly. The insects are much louder. So we have classes for insects, a bunch of classes for frogs, not enough. We also detect dogs barking, but we don't show you those. So it's trained on a whole bunch of other sources of sound, and if it knows those aren't birds, and so it basically ignores them. Same thing with human speech. Human speech usually looks pretty distinct enough that we can filter it out. Things that we still sometimes struggle with are like kids screaming that sound incredibly like waterfowl. But yeah, so we've trained these other classes to eliminate them.
Okay, I think you answered most of the next question, so I'll just ask the part that I think you didn't answer yet, which is the signal sent to Cornell a time domain or a frequency domain characterization?
So signal isn't actually technically sent to Cornell. So we're all running this stuff on Amazon Web Services. So we're running BirdNet in the cloud, usually, for the detection. And so what we upload is the raw audio file. And then the spectrogram is generated and sent through the neural net, and then the classification is made. So that's how, so even in this browser, when you switch audio files, it's generating the spectrogram in the browser with math, right? So there's FFT, Fourier transforms, and all sorts of fun stuff generating the spectrogram. I think someone else had also asked about scalings of the spectrogram. So they live in a very quiet place. And so they're probably able to detect sounds from much further away. And so they were asking about whether they could scale this to see the signals better. And so that's actually a good suggestion. So we've settled on settings like, how loud does it have to be dark yellow, or like light blue or dark blue. And so, but those can be tweaked so that you can kind of draw out the contrast. Kind of like the same way if you're a photographer, you might highlight shadows and highlights and change all of those sorts of things too.
Okay, so the next question is, do bird songs vary with the season? If so, does Haikubox take this into consideration?
So first of all, I'm not an ornithology expert. And this is going to be based on my experience. So, typically in the spring, there's going to be a lot more song being generated than you will get other parts of the year. But you can still hear the same songs at other parts of the year as well. But then other times you'll just get calls all the time from the same birds. What was the second part?
Does Haikubox take this into consideration?
So Haikubox, so the neural net has been trained on all sorts of different kinds of calls. So if you go look at, I should have cardinals. Where'd all the cardinals go? Yeah. So cardinals make tons and tons of these calls, right? The gajillion of these. Okay. But they also make, so I'm going to also show you one other thing. I need to go back in time because cardinals, so this is in Florida. Actually, do two things. So there's this calendar thing right here. And if you're in the view of last 12 or last 24 hours, you can see this calendar. So you can go back to any day in the past and see what they were doing. So I just clicked April 9th because I remembered cardinals, I think, calling a lot back then. Okay, so here's a different call, right? So you remember the other ones were these vertical. Okay, so the net has been trained to recognize, it's been trained on all of these different cardinal calls together. And so it basically knows to call any of those cardinals. So it can recognize both like the calls and the songs from the same species. Now you asked about seasonality. So one other thing that we do is there is a list of expected species in your area. And that list is updated weekly, and it's based on eBird sighting data. So basically, if it says, if there's a migrant that's coming through the area, so say you're in the Northeast and, you have dark-eyed juncos in the late fall, winter, and spring, it'll go, okay, I only expect them here. And then in the summer, it doesn't expect to see any dark-eyed juncos because they've all gone to Canada. If it detects a dark-eyed junco, we won't show it to you. We actually keep track of it, but we won't show it to you. So if you notice a bird that it is missing, please email us because often that is an inaccuracy in the species list. So if the bird if the bird is missing from your species list, we will never show it to you that week. And that's a quite easy thing to fix. So that's how the seasonal adjustments happen too, is that this filter of this expected species list is changing week by week through the year.
Okay, next question is volume represented in the spectrogram?
Yes. So volume is represented by color. So the quietest frequencies are dark blue, and then kind of the brightest yellow or red are the highest sound levels. So I think this, oops, no. Sorry, I'm looking, yeah, so this one you can see is a little bit louder. And actually, this one I moved here because it's a miss ID. It's actually a Nande parakeet, but so this yellow is the louder sound than the blue. And if you get something really close, oh, this one's loud. Like very close to your Haikubox, right? You can see how it's getting to this more orangish color. And then this red down here, that's traffic noise. So you can hear that as well. It's just this constant noise. Okay.
Okay. Yep. So I think this might have less to do with spectrograms and more to do with how it works. But so if there are a number of hits, regardless of confidence, even if they were all low, would you have high confidence that the identified bird was really there?
Not always. Sometimes. So one change we made a couple of months ago was on the homepage. If a bird has only been detected, say like once in the day, we call that low confidence no matter what bird it was, because often if a bird is there, it's going to keep calling. If you want to see the birds that are probably false detected the most on, if you go to the all page and go all the way to the bottom, right? So we've got 38,000 blue jays here. My guess is 99% of those are correct. But if you come down to these ones that have a handful, they may, especially if it's like a wading bird, I would really inspect the spectrogram and go look at eBird and compare them. I've certainly seen times and had really great experiences where it's been like one detection and it might be low confidence, but it was like real. So I think one was we had an American kestrel, I think last year, and I think we got like 3 detections and I'd never seen one. And then we just ran outside and we have these really tall concrete light posts and it was just sitting there on top of it. So the answer is sometimes, but not necessarily. So if it's like if there's a sound, whatever, like a truck backing up and whatever, for some reason, that beeping sound of the truck looks a little bit like a bird and it keeps beeping and we keep calling it low, then it doesn't make it any more likely. So you really have to go in and look at the spectrogram to try to assess.
The next question is there any way to enhance sounds from migratory birds at night?
It's a good question. So we were just talking about that last week in trying to detect nocturnal flight calls. So the net for most species wasn't trained on them, but for some, I think it may detect them. So there's kind of 2 challenges. One is often the birds are quite high, and so the sounds are quite faint. And our microphone is omnidirectional. So we're picking up sounds from, this way and up. And so a lot of the folks that are recording night flight calls will actually put their microphones into like flower pots or parabolic dishes and point them up. And what they're trying to do is increase the signal to noise ratio and picking up these really faint calls from very high down low. So we were talking about how we might be able to make something like a little attachment to kind of do that sort of thing. So, but that's totally at the preliminary stage right now. So yeah, it's something we're looking at.
Okay, so the next question is, what is the time delay between when the sound is picked up by Haikubox and the identification and notice goes back to the app and can be seen?
It's usually probably 2 seconds, 3 seconds. So there's a whole bunch of things that are happening. So So when the sound is detected, right, after that 3-second period is, and we think there's a bird there, we send that clip up to the cloud, and then the cloud basically has to decompress it, make a spectrogram, run the inference, and then write that out to a database. And so that is not always like, that's what, half a second to a second. And then if you're like sitting on the live page, there's an unknown amount of time before that updates. So that might be a second or two, because that has to basically sync the browser back into the back end. So, but usually it should be like less than 5 seconds. One thing you may notice on the live page is for some birds, especially the common ones, we don't send up an audio file for every single blue jay we hear. So, so if we detect like a blue jay, and then we'll actually count for up to a minute, however many blue jays we get, and then we send that as an audio file with the count that we detected. And so you can see that if I come here, and we only do this for the common birds. So like every warbler you get, every what you might consider an interesting bird you get. So if you look at blue jays here, right, there's 786 detections today. There are not 786 audio files for you to listen to, because people are not going to listen to 786 blue jay calls from one day. So that's kind of why what's happening here on these species. But for other species, like this osprey, all 10 of these detections should appear below here because we're sending every clip up. So it should be pretty quick, certainly less than 10 seconds for the whole process to go end to end. And then to some extent, it may depend on your internet connection speed too.
Okay, so the next question. So it seems like the only time to use the drop-down menu in Haikubox to say, no, that's not the bird you identified when you're labeling, is when we visualize it, because the neural net interpretation of sound alone would always, question mark, be better than a human only hearing it. Yes?
No. So our brains are really good. And so I think between listening and looking, right, you can use that to label. It is super helpful. Like even like doing this blue jay is correct and saying yes, that's sort of helpful to us because now we have another label that we can use in retraining. So even if it's a common bird and you can manage to do a few of those a day, that's awesome. There will be times where, like osprey for sure, I may not be sure about this one when I listen. It probably is, but often, like the one thing that you have that we don't is you are like often where your Haikubox is. So you also have, all this knowledge about what birds are around your house. And so that sets some level of expectation that it might be there. So you can use that information in labeling it as well. So sometimes the net is better than us, especially with the call type signals, but other times no. Like listen to an example from eBird, see if they match up, and then use that to base your labeling on. And if you're not sure, just click not sure, and you can just go, yeah, I'm not sure. And then at least we know like someone looked at it and that's a tricky sound to actually ID. I don't know if that answers your question. So, Amy's labeled thousands upon thousands, probably maybe 10,000 sounds. And so it can be exceedingly difficult for some sounds. And then other sounds are extremely characteristic, like, the Carolina wrens, like so easy once you get used to them. But then there's other ones, like I've been looking for a scarlet tanager all summer, and it picks them up and I compare it and it looks right, but I still haven't seen them. So, and I'm like, yeah. So yeah, so I mean, do your best. The way we get better is having a lot of different people doing labeling from different locations, and it's okay to mislabel occasionally. The neural nets kind of figure that out.
So the person who asked that question said yes, that answered her question.
Okay.
Okay, so the next question, how should we think about the enhanced option? How does it filter out other sounds?
So what it's doing, so it's actually doing, so this is happening in the browser, and so let me just play this one. And so what it's doing is it's looking for signals in the spectrogram that are changing kind of quickly in time. And so like constant signals like this traffic noise, or if there were insects here, what it's doing is it's actually going into the spectrogram and going, well, that's not changing. I'm going to knock that down in level. And then, so it's doing it on the spectrogram. And then I am like inverse FFTing the spectrogram back into an audio signal. Let's play that. Right, so you could hear it, and it picked out this thing and this thing. Sometimes it will sound like you're listening to R2-D2 from Star Wars, and that's because like just some like little random things actually get emphasized. But it's basically trying to remove these constant tonal things. Let me see if I can find any. You know where there would be some. Sorry, I'm trying to find a place with insects. So it's basically here. Let's see if this one does it. Okay, so you see this constant line here. That is crickets, and then this one here is crickets, and then here's the cardinal call. So if I play enhance, so most of the time it was knocking down all of this background noise. Although I did hear like this particular cricket or something here actually got easier to hear. So that's what it's doing. It's my attempt to try to improve the signal to noise ratio to make it easier to hear. But sometimes it also makes it sound weird. So this one again. Okay, so there's a black cap chickadee you can hear up here, but there's also these two bands of insects. Okay, so you could hear the chickadee pretty well, but before it, there's like this whoop, whoop, and then it's like something in here that it was basically amplifying. So if you hear like these weird Star Wars sounds, just ignore them. But it can help you actually pick out a signal that is very faint. You don't need to use enhance if if you come here. Let's see if I can find the loud one. Right. So this tufted titmouse signal is pretty loud, although it's also pretty high frequency. So I don't think enhance is going to help this one that much. Yeah. So think about it as it's trying to improve how easy it is to hear, but sometimes it garbles it. So.
Okay. So I can probably answer this one. What's the difference between the two different sizes of Haikuboxes? Does a 5-year have a better microphone? And the answer is no. We started out with the larger version, and then we wanted to make it easier to assemble and use less plastic and just be smaller in size and easier to ship, etc. So David basically rearranged everything in the inside. It's all the same stuff though. What? Oh, there they are.
So this is the microphone from the larger one. So it's on a separate board. On the newer one, the Chirp, the microphone is now here. You can pop open your Haikubox and look at it if you want. Just make sure you seal it up right. So the microphones are the same. It's just we are trying to reduce basically how much stuff we're using to make them. So yeah. So those ones all work in the same way. If you got one of the like earliest ones when we first started, those work in a slightly different way because those have tiny little computers in them. But that you would have gotten that like 3 years ago.
Yep. Okay, next question. Hello, greetings from Mexico. A couple of weeks ago, I received my Haikubox. I'm learning a lot about recordings and spectrograms. Sometimes my Haikubox does not identify certain species from my area. How can I make it include those species, for example, a violet-crowned hummingbird? And that goes to some of what you were talking about earlier about
so
not being on the list.
Mm-hmm. Yeah, so our lists for outside, so our lists are decent for US, Canada, and Europe. They're not decent for Mexico, Central America, Caribbean islands. And so if you have one in Mexico, just send me an email about which one it is, and we can look. There are things we can do to detect more species, whether it's updating the list or potentially running it through a different neural net. So just let us know.
Right, and some of those places like Mexico, we've just recently sent some to Kenya. One's going to Brazil. Those are places we're testing, and David's working to make them better so that, because the birds don't stay in North America, they go and they don't stay in Europe, they go other places. So we want to be able to identify them wherever they are migrating to. So, and I have one more question. So this question was maybe cut off at the end. So we'll see if this makes, if there's enough information here for you to provide an answer. I really love my Haikubox. I'm in Austin, Texas, and my box has 32 species at high confidence. What are your thoughts on what I call ghost birds? I have 14 feeders and 4 bird baths. I've never seen a blue-gray gnatcatcher, American goldfinch, and eastern phoebe, but I get alerts for them. Oh, so maybe it was the whole question. There was no period at the end, so I thought it got cut off. But what do you think about those not being?
So one thing that you can do, so so your ghost birds are potentially misidentifications of other species. That part of Texas can be a little tricky because there's some species shifts over very small ranges. But one thing you can do, let me just find one that maybe like this. Let me find a hawk. There. Okay, so this red-tailed hawk, that's low. Maybe. But I look and I go, oh, this is at 547. And I know that this guy up here, the blue jay, can sometimes mimic sounds. So I might go look like, okay, what was the blue jay doing around 546? And basically look close in time and see if you can find another bird that it actually is correctly identifying that looks the same. I have a really good example for you that I noticed this summer. Where are we going to go? Hold on. Okay, so I'm going to look for worm-eating warbler, and here's how I'm going to find it. So I'm going to my all page. In the select species thing, you can start typing and then click, and then it's going to find the worm-eating warbler. So I'm on the all page, and then I'm going to look at my daily chart and go, okay, I had a whole bunch between, and you can also zoom in on this chart somehow. There we go. Like around July 8th, 9th, 14th, 17th. I'm going to come back, look at my calendar, come back to July. I think I said 9th. So I've never seen a worm-eating warbler. And we were getting lots of detections of them. But one thing I noticed on this page. Here we go. So you can also, if you're on a browser, you can just use the search tool to find stuff on the page. I look at this song, but look who's here next door is the chipping sparrow. And I look at that one and I go, huh, it's the same thing. So, and we had feeders up and we had chipping sparrows at the feeders. We know chipping sparrows were around and calling. And so this is a mis-ID. If you hop over to eBird and look at worm-eating warblers, they look a heck of a lot like chipping sparrows. And so like improving this ID is kind of one of the ones on what we call our whack-a-mole list. But it's going to be incredibly difficult. Like I was going back and forth and I'm like, I don't know if I could do it. So one thing you can do for your ghost birds is look around it, but click to the spectrogram and go, well, you know, does that blue-gray gnatcatcher actually look like some other sound? And then you might be able to go, well, so is worm-eating warbler correct? You know, no. Is it chipping sparrow? And click submit. And then we have it. And having like notes like that in there is super helpful for us because we're basically going through and we find the bird, like the birds that we're gonna try to make better first are the ones that have the most labels as wrong. And so if there's something driving you nuts and you label it a ton, you might bump up a fix for it faster. So I hope that made sense.
Yes, sorry, somebody had asked for the web address for Haikubox instead of the app, so I just shared that in the chat.
Yeah, and
you can always reach us by email at info@haikubox.com.
There's no difference between the phone app and the browser-based web app, except two things. On the browser-based web app, you get to download the audio files and save them and do stuff with them. On the phone app is where you set up the notifications. Those are the only two differences. Otherwise, it is the exact same code and stuff underneath. So when I update, like add a new feature or change something, it changes everywhere at the same time.
So we're at 8 o'clock. I'm just about to end this, but one person did ask as kind of a follow-up. I'm thinking it's kind of a follow-up to what you were just talking about labeling. When people, the question is, what does any of the programming do relative to likely incorrect identifications by us, the users? So how do you use that information?
So it is not acted upon immediately. So if you label something wrong, and it's always wrong, it's not going to get fixed immediately. We've talked about ways of dealing with it, but if it's driving you nuts, like on this worm-eating warbler, I can just turn off show. And when I come back to this page, it won't show me the worm-eating warbler anymore. So that's one thing you can do there. But it's not fixing the problem. So what we do, so I'll give you an example. So our top misidentified species a while ago was Canada goose, because there's a lot of other household sounds that sound like them. We actually made another neural net just to tell Canada goose from other stuff. So we actually run it through BirdNet, and if it comes out Canada goose, we actually run it through another net that actually reduces the amount of false detection. And what we've done is we took all of your labels for Canada goose that were wrong, those got stuck in one batch that's like not Canada goose, and then all the ones that you said yes for Canada goose got stuck in another bin. And then we train up a pretty small net that can actually distinguish those and basically get like 90% better on that species. So that's what we're doing as we go through, but we need like at least 1,000 labels of what's wrong and what's correct to be able to do that. And so we just go with the species that has the most labels, as in like, this is not, for example, cedar waxwing. That is our next top one. And so we'll use that to improve it. One other thing that actually happened over the summer is we pushed there's actually a small neural net running on the Haikubox that's detecting blue jays and things. And we improved that so our owl detection is better. And so we've also been working on so we were missing a fair amount of owls, and so that should get better. And then we're also trying to improve screech owls because a lot of sirens were being false detected, like police sirens were being false detected as screech owls. So that's how your labels get used, but honestly, it takes months. And it is usually me and Austin, our AI programmer, he's a programmer of AI, to make implement it. And so, yeah, so that's how they get used, and it's not going to be instantaneous. This is a thing that will slowly get better over time, but ideally it doesn't ever get worse. So,
all right. Well, we'll close on that. Thank you to everybody who is here. I'm grateful for your time tonight. Thank you so much.
yep, thank you.